In this video, we will talk about music genre classification. This is our agenda. Firstly, I will talk about the introduction. Music classification is an interesting problem with varied applications. However, music genres are inherently subjective because they are hard to systematically and consistently describe. To overcome the difficulties, we read a lot of papers and implement our music classification in the end. As the picture 1 shows, we used the traditional machine learning approach to automatically classify different music genres from audio fields. We will classify these audio fields using their low-level features of frequency and time domain. During this process, we use MFCC technique. We design 3 models, KNN, GMM, and SVM to finish the classification and test the performance. Next, I will talk about the dataset. We use Citizen Genre Classification dataset. The audio tracks in this dataset have similar size and similar frequency range, which are what we needed. The 10 classes are as the picture 2 shows. We divide the data into training dataset and testing dataset, which are 90% and 10% of data, respectively. Furthermore, each class has the same number of samples in training and testing. Then, we need to use MFCC technique to extract audio features, as the picture 3 shows. Since the audio signals are constantly changing, at first we divide these signals into smaller frames. Each frame is around 20 to 40 long. Then we try to identify different frequencies present in each frame. Next, we separate linguistic frequencies from the noise. To discard the noise, it can take discrete cosine transform of these frequencies. Using DCT transform, we keep only a specific sequence of frequencies that have a high probability of information. To implement these, we use the library Python speech features in PyCharm. Now, let's talk about the model KNN. The KNN algorithm assumes that similar things exist in close proximity. In other words, similar things are near to each other. Picture 4 shows the KNN algorithm steps. The value of the nearest neighbor's key and the distance matrix can affect the KNN performance most. Key is highly dependent on the training data. So there is no optimal choice for all datasets. In most cases, a smaller key creates a complex model with rough decision boundary and increases the accuracy of KNN. But when key is too small, the model becomes more sensitive to outliers or noisy features if the class's boundaries are not clear, which means overfit. On the other hand, for a larger key, it can create a simple model with smooth decision boundary, which suppresses the effect of noisy features but leads to a higher misclassification rate. When K is too large, all testing points will belong to the same dominant class, which means underfit. There are several distance functions used to compute the distance between the two data points. Commonly used distance functions include Euclidean, Manhattan, Chebyshev, and so on. Now let's see the code. Well, for this one, distance function is to construct the distance matrix. This function, getNeighbors, is to get the distance between feature vectors and find the neighbors. The function nearest class is to identify the nearest neighbors. For this, it is to extract features from the dataset and dump these features into a binary date file, my.date. This one, my.date. Then let's come back. We run the code and get a good result. For KNN, its accuracy can achieve about 70%. KNN is very simple and easy to implement, but as the number of examples increase, it gets significantly slower. In our project, it runs 13 seconds. Now let's do some experiments. We modify key values and find the optimal key, which makes the performance best. Key should be odd number. We try 7 values from 3 to 15. The accuracy here is defined as correct number of atoms divided by total test number of atoms. In the code, we modify this value. Let's see the result. As the table 1 and the picture 5 show, different k make different predicting accuracy. When k equals to 7, we get the best result. The performance is best too. Finally, we do the evaluation. We hope to evaluate the performance more specifically. We use 4 parameters: accuracy, precision, recall, and F1 score. At first, we will introduce the obfuscated matrix of classification results. TP, true positive, it means the atom is predicted as a positive class, while it's actually a positive class. Fn, false negative, it means the atom is predicted as negative class, while it's actually a positive class, and FPTM are similar. We use TP, Fn, FPTM to compute the accuracy, recall, precision, and F1 score. The formulas are on the page. In order to test the performance of our model by the above evaluation parameters, we need to test the music classes one by one. Let's see the codes. The evaluation function is here. We can modify the index to modify the music classes. Now come back. After our testing, we can get the following result as the table 3 and the picture 6 show. We find in the 10 music classes, the jazz music can be predicted best. The 4 parameters all look good in this class, while the third class, country music, makes the worst prediction. All parameters of it performed bad.
Gaussian mixture model is commonly used in acoustic learning tasks such as speech or speaker recognition, since it describes the varied distribution of all the feature vector. GMM assumes that the probability of a feature vector X belonging to the model is shown here. Therefore, GMM is merely a weighted combination of multivariate Gaussian distribution, which assumes feature vectors are independent. Actually, we use diagonal covariances since the dimensions of the feature vector is independent to each other. GMM can describe the distribution of feature vector with several clusters, as shown in picture 7. The training of GMM is the process to find the best parameters for mu I, sigma I, and omega I, so that the model fits all the training data with maximized likelihood. More specifically, expectation maximization algorithm is used to maximize the likelihood. The two steps of one iteration of the algorithm in GMM training case here are E-step and M-step. In E-step, for each data point, estimate the probability that each Gaussian generated it. This is done by direct computation of using the equation of previous slide. In M-step, modify the parameters of GMM such that maximize the likelihood of data. After training, the model can give the score of fitness for every input feature vector, measuring the probability that the vector belongs to this model. We implemented this machine learning classifier by using Python's sklearn library. Sklearn mixture GMM is a representation of a Gaussian mixed model probability distribution. This class allows for easy evaluation of sampling from and maximum likelihood estimation of the parameters of a GMM distribution. And here we vectorize the data and then run PCA to reduce vector size to 900. The function here computes accuracy given the predictions and real labels. N classes is equal to 10 because there are 10 Java classes. We try GMMs using different types of covariances, including full, tag, spherical, and tight. An iter is number of EM iterations to perform. Since the maximum number of it is usually 100, we change the parameter ranging from 5 to 100, including 5, 10, 50, and 100. Since we have class labels for the training data, we can initialize the GMM parameters in a supervised manner. And we train the other parameters using the EM algorithm. And here we get predictions of training test set. And this is for testing set. Table 4 and Picture 8 show our running result, and the performance here is separated into two accuracies that evaluate predictions of training set and testing set. We can see that the performance is the best when covariance type is set to be full followed by tight. However, the last two conditions show very bad performance. From Table 5 and Picture 9, we can draw the conclusion that when 5 EM iterations are performed, the algorithm shows the best performance, and with an iter increasing, the accuracy becomes a little better, but it is still very bad. Support vector machine is a well-known supervised machine learning classification technique. The objective of a SVM algorithm is to construct an n-dimensional hyperplane, which can be used for classification or regression. Actually, a good hyperplane is the one that achieves the largest distance to the closest data point of a particular class. This can be better explained with the help of Picture 10. Here, the red and green dots represent two different classes of the dataset. The support vectors are the points which help in identifying the hyperplane, And in this scatter plot, the green class provides two support vectors, and the red class provides one. Using these support vectors, we draw lines passing through them that would distinguish the data from the other class. However, for most scenarios, the data is not scattered in a manner that would be linearly separable. Also, a line might not be used for always defining the hyperplane. For a nonlinear distribution of data, SVM has a concept of kernel trick, which is used for defining the optimal hyperplane. The kernel trick converts the given data into a higher dimensionality space to achieve a linear separation between the points. Picture 11 shows how the hyperplane changes from a line to a plane, depending on the dimensionality space. It represents a simple kernel function which uses the formula xy x multiply y to obtain a linear separation of data. This is a simple representation of how kernel tricks work. We use the class SVC from the package sklearn_svm. In the experiment, we implemented SVM using different types of kernel, including linear, RBF, poly, and sigmoid. Table 6 and picture 12 illustrate the running result, and the performance here is evaluated in the same way with GMM. We can note that both linear kernel SVM and polykernel SVM perform well, and they enjoy significant advantage in performance compared with the algorithm with the other two types of kernel. Picture 13 shows the running time of the three models. According to this, we could infer that both GMM and SVM perform very fast. In contrast, KNN is quite time-confusing. In conclusion, the study is broadly divided into three parts: audio acquisition, audio feature extraction, and audio classification. In the second part, we did pre-process, and it is an extremely crucial part of the research. MFCC is used to acquire usable training and testing datasets for the next stage. Now, considering the three models, the simpler and more naive approach, KNN predictably did worse than the more sophisticated algorithm, GMM. However, we expected better performance from SVM based on the papers we read, so the lowest accuracy came as a surprise. A large part of this is probably attributable to the different pre-processing methods used before. However, when it comes to running time, it could be definitely concluded that GMM and SVM are quite time-saving compared with KNN. Besides, most learning algorithms had most difficulty recognizing metal and country. This corroborates the idea that qualitatively these two genres are not so extinct. Furthermore, after our experiments using these three training models, we could get each of the optimal solution. Specifically, KNN performs best when k is equal to 7. When it comes to GMM, using full covariance and performing 5 EM iterations, the algorithm reaches the highest accuracy. At last, both linear kernel SVM and polykernel SVM show good performance. And that's all. Thanks for watching.